Welcome. We were looking at the solution to this example problem which involved the use of the Clausius-Clayperon equation. The problem itself was isopropanol is evaporating under pure substance conditions at 87.4 degrees C and 1 bar. Assuming equilibrium conditions, what is the change in pressure per unit change in temperature that is needed to maintain equilibrium, and the latent heat of vaporization of isopropanol is given. We saw that we needed to use the Clausius-Clayperon equation to get dP dt, which is the quantity that we need, and we also saw that realized that the values of L and T are given, and therefore if we know delta V, which is V of the gas or V of the vapor minus V of the liquid, the molar volume differences, then we can find dP dt and get the quantity of interest. And we also noted or recognized that the way to go about finding out the volumes of the gas and the liquid was through the use of an equation of state, a suitable equation of state. Now let me give you some more details and then let you work out the actual numbers. For this particular problem, since we have seen the Redlich-Kwong equation of state earlier as some sort of an improvement over the initial equations of state, we will use the Redlich-Kwong equation of state here. And if you recall what we did in module 3, we actually needed different formulations of the Redlich-Kwong equation of state to estimate the vapor and liquid molar volumes, because the formulation for the vapor volume had a V minus B term, and if we had used that with an initial guess of V equals B, then that term would have completely gone to 0, and we would have completely eliminated that term and not had the benefit of the contribution of that term into our estimations. Also the vapor volume estimated was for a different set of temperature and pressure. If you recall, we had estimated the vapor volume in module 3. We cannot use that here because that was for a different temperature and pressure. If you recall correctly, it was around 200 degrees C and a pressure of 10 bar. At that pressure, it is going to be a complete vapor. It is not going to be in a state of equilibrium between the liquid and vapor phases. Therefore, and here in this problem, it is vaporizing, which means it is in a state of equilibrium between the liquid and vapor phases. This point is somewhere along the vaporization line in the PT diagram. Therefore, we cannot use the value that we calculated earlier. We will have to do the estimations all over again, and therefore let us start with the iterations. This is the iterative form that we found to be most useful for finding out the vapor volumes. Vn plus 1 equals RT by P plus B minus A into Vn minus B divided by T power 0.5 P into Vn into Vn plus B. So we saw that if we put in a guessed value of Vn, we get a calculated value of Vn plus 1 by calculating the right hand side, and if we find out the difference between the calculated value and the guessed value to be close enough, or the difference to be negligible enough, then we can stop the iterations. Negligible enough, we said it should be, let us say, within 1 or 2% of the guessed value. The value of the Redlich-Kwong equation constants A and B can be obtained from equations 310 and 311 in module 3. We have already done this as a part of an earlier solution in module 3. I would like you to go back and revisit that if you have forgotten, and to get back into the frame of mind for solving this particular problem. A was 0.42748 r squared Tc power 0.5 by Pc. If you substitute the values 0.42748, 8.31 for r squared, 508.3 for Tc the critical temperature, power 2.5, Pc was 47.62 into 10 power 5, which turns out to be 36.11 Pascal per meter cubed per rather meter cubed per mole the whole squared. This is the unit of A, and B is 0.08664 r Tc by Pc. If we substitute the values, we get 0.08664 into 8.31 for r, 508.3 for Tc, and 47.62 into 10 power 5 Newton per meter squared for Pc. That turns out to be 7.685 into 10 power minus 5 meter cubed per mole. Therefore, now we have the A and B values, we can iterate the Redlich-Kwong equation written appropriately for iterations to get the vapor volume, which is this. This is the equation that we are going to use. We get Vn plus 1 equals 2.995 into 10 power minus 2. This is RT by P plus 7.685 into 10 power minus 5, which is B, the value of B, and this is minus A into Vn minus B divided by T power 0.5 P into Vn plus B. Now, this Vn is our first guessed value, and we said we could use the ideal gas equation value for the first guess, because this is a vapor phase. So, if we do that, first estimate the ideal gas equation, then use that as the first guess, and then calculate the value, find out the difference between the values, see whether it is acceptable. If it is not acceptable, use the calculated value as the next guess value, and so on and so forth. Then we can get the solution. And what I have done here, and we also saw that these iterations can be done on either a hand calculator or a spreadsheet or a computer program, and you can do it whichever way you want it, but what I am going to show you here is the use of a standard spreadsheet for doing these calculations, and I will show you one and probably let you do the other. To look at the spreadsheet, this is the first column is the guessed value, the second column is going to be the calculated value. Guess value, our initial guess value is going to be 0.02995, which comes from the ideal gas equation, PV equals RT, therefore V equals RT by P, and that is going to be 0.02995. You can recall this, we had, just a second, I had given this calculation, yes, this RT by P is 2.995 into 10 power minus 2. Now, this is nothing but our ideal gas volume. Therefore, this is what we are going to use as the first guess, 0.02995 this value, and then if we calculate all those RT by P plus B and so on and so forth, whatever was in the right hand side, we would get 0.02936,793. I mean, rather, do not have to worry about too many things. The way we calculated is given here. This is the these are the terms on the right hand side. I just substituted these terms, 0.02995 I have approximated as 0.03 minus the A into A3, this happens to be the volume that is guessed, minus B divided by Vn into Vn plus B. So, this turns out to be 0.0293 and so on. So, now the main thing is what is the percentage difference. it turns out to be 1.94%, okay, which is reasonably fine. In fact, we can stop our iterations here if about 2% is allowed, but let us go a little further since we seem to have hit upon the value within one iteration. Let us go about further and improve the accuracy of our value, and also this helps to demonstrate how to do the iterations. Now let us assume that this is not an acceptable percentage. Let us say that we are looking for a percentage which is less than 10 power minus 3 or 10 power minus 4, yeah, 10 power minus 3 is a good value. So we take the calculated value, put it into the guessed value, calculate the value again, this is the same equation that was used to calculate the value. Now you find that the guessed value was 0.02936 so on, and the calculated value turns out to be 0.029355 so on, and the percentage difference is, the percentage difference was calculated as A4, which is this, minus B4, which is this, the difference divided by A4 into 100, that turns out to be 0.042, which is a very small percentage acceptable here, but we said 10 power minus 3 in this case, but still not 10 power minus 3 here. So we go through the next iteration, 0.029355 so on, we put in here, we calculate the value again here, they can simply calculate the value by control D, it copies the formula here and calculates this value. Here it turns out to be 0.029355197, very close to this, and actually the percentage difference turns out to be 9.27 into 10 power minus 4. This is definitely less than 10 power minus 3, therefore this becomes acceptable and we can choose this as our gas volume. So that is what we have done. We have chosen V vapor as 2.9356 into 10 power minus 2 meter cubed per mole. Now this is only the vapor volume, we still need the liquid volume. The liquid volume we said requires a different framework, we have already seen this, so I am just going to state it here. This was the way in which we have cast the Redlich-Kwong equation by an appropriate manipulation to overcome the difficulty that was posed by the previous iterative formulation, and we have seen this earlier equation 314, you can go back and check how we got this, and to be able to do this I think we have all the values, we have B, we have RT, yes, A, and as long as we keep substituting the appropriate guessed values we will get the calculated value. And we said that the first guessed value, first good guess would be the value of B, which represents the volume of molecules that are present in the liquid, present in the pure substance. And in a liquid form these would be close together, and therefore the volume of molecules can be approximated to the volume of the liquid, and that is how we take B as the first guess here. If we do that, what I would like you to do now, I am going to give you another 20 minutes this time, because these are calculations and you are going through this. Please set up a iteration scheme on the spreadsheet that I have shown earlier and do the calculations, use B as the first guessed value and see how you get. I will show you the calculations when we come back. Please go ahead and do this, this will help you get used to the iterations, and spreadsheet is a nice way of doing the iterations. Go ahead please, 20 minutes. Okay, you would have had a chance to first calculate the right hand side, substitute the B value and also set up a spreadsheet iterations, set of iterations, and you know hopefully gotten the final value. In this case it takes about 5 or 6 iterations to get to the final acceptable final value. The details are as follows: Vn plus 1, if you substitute B and so on and so forth, it is going to be this value B squared plus BRT by P minus A by PT power 0.5 1 by the whole thing is going to be minus 59901.4, and then Vn cubed minus 2.995 into 10 power minus 2, which is RT by P Vn squared minus AB by Pt power 0.5 1.462 into 10 power minus 9. Now let us look at the spreadsheet that I have. You can compare it with the spreadsheet that you have. Now this is the first column is the guessed value, the second column is the calculated value, the third column is the percentage difference. These are the vapor values. Now let us look at the liquid values. First B 0.00007685, and then the calculated value is 9.81 to 10 power minus 5. The percentage difference is 27.7. This is clearly unacceptable. Therefore, we put the calculated value, you know, the calculations are given here into the this is that was a previous one. The calculation, this was the equation that we saw for the liquid volume iterations, 59901.4 minus 59901.4 into the one inside the brackets. Now we substitute the calculated value as, or take the calculated value as the second guessed value. The calculated value happens to be 0.0001 and so on. The percentage error is 6.78, still clearly unacceptable. Therefore, we do another iteration, take the calculated value, put it into the next guessed value, and here the percentage difference comes down to 2.3. The next time you do it, the percentage is somewhat acceptable, 0.85, and then if we want to continue and improve our accuracy, one more iteration comes down to 0.324, and we will stop here. You could have even stopped here. Let us do a couple more and we will stop at 1.086 or 1.086 into 10 power minus 4. and 0.086 into 10 power minus 4 meter cubed per mole. So this is how slightly lengthy procedure to, but it is an iterative procedure, explanation takes time, but if you do it yourself it is much faster. So we have the vapor volume and the liquid volume, the molar vapor and the molar liquid volumes. Substitute this back, take the difference between the two, it turns out to be 2.9247 into 10 power minus 2 meter cube per mole. This was the only thing that was needed for us to get dP dt, and substitute this, dP dt equals L by T delta V. L was 44 given earlier, T 360.4 the temperature of interest, and delta V 2.9247 into 10 power minus 2, we get 4.174 Pascal per Kelvin. So this is the amount of pressure for a unit change in temperature that is required to maintain equilibrium when this process is taking place. That is one of the interpretations of the left hand side of the Clausius Clayperon equation. Okay, let us go on to the next thing, which is vapor liquid equilibrium. The last example was also an example of vapor liquid equilibrium, but that we saw as a specific case of phase equilibria in general, and the Clausius Clayperon equation could be applied to phase equilibria in general, and we came from that angle, and we are going to look at something more in detail for the specific case of vapor liquid equilibrium in what follows now. Let us first look at the vapor and liquid phases of a pure substance at equilibrium. This we had said earlier, I would like to re-emphasize because I see a lot of confusions when students approach this. So let me state this again, just repeat whatever I said earlier. For example, the pure substance could be just water, but not the water and air system. It is easy to confuse between the two, because water and air is what we come across very commonly, whereas we are talking of a pure substance here which could be just water, although the multi component water air system could be more common as just mentioned. This is the vapor liquid equilibrium, and as we have seen earlier, the conditions of equilibrium need to be valid. The conditions of equilibrium, as we said, was the temperatures need to be equal across phases, the pressures need to be equal across phases, and the chemical potential of a species needs to be equal across phases, and of every species needs to be equal across phases. So the conditions of equilibrium phi 1 to phi 3 say exactly what I just said, and also we are going to use subscripts V for the vapor phase and L for the liquid phase, and also we are going to use SAT for representing saturated values of temperature, pressure and so on, which is applicable at the vapor liquid equilibrium conditions. So this is the first condition, temperature of the vapor phase must equal the temperature of the liquid phase, and this is the saturated condition, therefore we can say must be equal to say T sat. This is equation 524, and the pressure of the vapor phase, the second condition, must equal the pressure of the liquid phase, and say that is equal to P sat 525, and the chemical potential, in this case only water is present, therefore the chemical potential of water in the vapor phase must equal the chemical potential of water in the liquid phase, and that is the only substance present in either the liquid phase or the vapor phase, there is no other substance present, and that is equation 526. Now what we are going to do is we are going to take equation 524 and 525, which is the equality of temperatures and the equality of pressures, to be a given whenever we talk of equilibrium. In other words, we are not going to explicitly state this every time, this is understood every time that we mention it. Therefore, we will be only concentrating on this particular equation from now onwards whenever we talk of vapor liquid equilibrium. This is a pure substance, and we know that from the condition of equilibrium, equation 526, mu of the pure substance in the vapor phase equals mu of the pure substance in the liquid phase. Therefore, we can use this equation 3.1b, which is the expression for the chemical potential, and expand that as mu equals mu naught plus RT ln F of the pure substance in the vapor phase must equal mu naught plus RT ln F, the fugacity of the pure substance in the liquid phase. Recall this from module 3, mu equals mu naught plus RT ln F, that is what we have written here. This is for a pure substance. Therefore, it is quite easy to see mu naught cancels, RT cancels later. Therefore, ln Fv equals ln Fl, and therefore, Fv equals Fl. The fugacity of the pure substance in the vapor phase must equal the fugacity of the pure substance in the liquid phase, and let us say that we are going to call it as the fugacity of the saturated or the saturated fugacity value. We will call this equation 527. Now, from equation 3.1c, you can go back and take a look at it, what it exactly says. I am going to restate it here anyway. It said that F by P was defined as the fugacity coefficient phi, and equation 525 is Pv equals Pl equals Psat. Therefore, we can write phi v Pv equals Fsat, or phi sat Psat. Phi v is Psat, phi v is nothing but the phi value under the saturated conditions in this particular system, which is vapor liquid equilibrium. P is Psat, and therefore, that equals Fsat. We will call this equation 528. The previous development, F by P equals phi, and therefore, since F v equals F L, we had expressed the fugacity in terms of phi and P here and got F sat, and finally expressed it everything in terms of the saturated value, and all this was for a pure substance. Now, let us go and look at a mixture of pure substances for a multi component system, that is. For a multi component system, the equality of chemical potentials of the components in the two phases is the condition. What I would like you to do in the remaining part of this lecture, and you can take this as homework, is to do the same development. Now, this is a good exercise, do the same development and come up with useful relationships the same way as we did for a pure component system, but you need to do it for a multi component system. Okay, can you go ahead and do it? I will give you the rest of the class, which is about 3 minutes left, and as a homework. When we come back, I will show you how to go about doing it. Go ahead, please.